So let's now consider the case of what happens when we put friction back into the system. The thing is, we already know what the homogeneous solutions are. Let's go back a few pages and notice that we've already solved this differential equation in various cases. And here are those solutions. On the one hand, certain cases we get decaying oscillations. In other cases, we get decaying exponentials, or decaying functions that look a lot like exponentials. Maybe there's an extra factor, but still the key word is they're decaying. So interestingly, not only do we know all of these solutions, these homogeneous solutions, we know that they all decay exponentially. So in terms of the long-term behavior of a system that has friction and external periodic forces, these homogeneous solutions basically don't matter. They're called transients, and they just don't affect the long-term behavior. Okay, so if we're interested in the long-term behavior of the solutions to this differential equation, we just need to look at the particular solutions. So we just need to find a particular solution to this differential equation. And we have a method for this. We have undetermined coefficients, and you're welcome to do that, I suppose. The problem is this can be hard in some cases, and certainly in related cases it's definitely hard. We're going to discuss here a really clever and valuable method to simplify this problem, and that is to consider a related equation. We're going to consider what I'm going to call the related complex equation that looks like this. So I claim that is related to this. Now you'll notice that the coefficients are the same. Same coefficients on the left-hand side. I'm calling these solutions Z instead of U. Okay. The other thing you might notice is that this right-hand side is exactly the real part of that right-hand side. That's going to turn out to be really useful. Okay, so turns out that solving this equation is going to help us solve the original equation. Now, the details of that are something we need to talk about, so I'll flesh that out over the next few minutes. One might ask, so what? And the big point is that this is actually easier. So you can see why this is actually an easier equation to solve by looking at the right-hand side and thinking about what the form of your guess would be. The form of your guess here would be, well, just an exponential, a single exponential term. On the other hand, looking at the right-hand side over here, what would be the form of your guess given this right-hand side? Well, you'd have a sine term and a cosine term. So you'd have two terms, and therefore you'd have to solve a system and solve for both of the coefficients. There's just more work to be done. This is a more desirable question to solve. Okay, so let's presume that we know how to find the solutions to this. Worry about those details in a little while. And ask, though, given that I can solve this equation, given that I know what this Z is, how do I figure out what U is? Okay. All right. So this Z function is going to have a real part and an imaginary part. Let's call them U and V. We've already observed that this right-hand side function has a real part and an imaginary part, the real part being familiar. And let's rewrite this differential equation now. That differential equation is just this. Okay. All right, well, plugging in what I know, plugging in that Z is U plus I of E, and expanding by linearity, the left side turns into that. The right side we've already observed is that. And so my differential equation becomes this. Well, the great thing about this equation is I see that there is a very clear real part of the left side of the equation. There's also a very clear real part of the right side of the equation. And if I have complex equals to complex, then the real part has to equal to the real part. Likewise, there's a very clear imaginary part on the left and on the right. And imaginary is equal to imaginary. So the wonderful result here is that, looking at the part we're interested in, is this. Notice that this is exactly that. So effectively then, if you can solve the complex equation, if you can solve that complex equation, the real part of it is the equation you're actually interested in. And specifically, the solution that you're looking for, the U that you're looking for there, is just the real part of the complex solution that you found. Okay, neat trick. Let me show you a different point of view on this, a little bit more blunt. Again, suppose we have a complex solution, U plus IV, all of these being functions of t. Specifically, that's a solution to our related complex equation. And now let's actually write out everything in this equation by separate real and imaginary components. Now, for convenient layout on the page, I'm going to represent z as U plus IV, written sort of vertically. So the real part's on top and the imaginary part's on the bottom. Well, then likewise, z prime, etc. Okay. Well, we have a neat fact, and that is that if two complex numbers are equal, then their real components are equal and their imaginary components are equal. And therefore, if this whole differential equation is true, then what you might call the real part of that differential equation is a valid equation, and what you might call the imaginary part of the differential equation is a valid equation. So, said differently, when you take derivatives of a complex valued function, the derivative of the real portion is the real portion of that derivative. And the derivative of the imaginary portion is the imaginary portion of that derivative. So, said differently, real stays real, and imaginary stays imaginary in the differential equations. It's almost like, in fact, it's very much like saying that inside of this differential equation there are actually two parallel, separate equations. There's the real differential equation inside of this, and there's the imaginary differential equation inside of this. So if you solve this complex equation, you're kind of solving two differential equations, one of which is actually the one you're interested in. The real part is the one that we're actually interested in for the moment. Okay. All right, different point of view on the same thing. All right, side note, if what you were interested in was a right-hand side that was a sine omega t, you'd use the same related complex equation, and note that it's the imaginary portion that you're interested in. All right, this is a really wonderful trick, and I encourage students to be on the lookout for opportunities to take advantage of this. When you have a right-hand side that has trig in it, very often you can view that as being the real portion of a real portion of a complex valued function that, while complex, is actually simpler to work with. And if you solve that related complex equation, then you can interpret a solution to the real equation. Okay, so now let's get back to our business at hand. Our goal was to solve this differential equation. Note the right-hand side is a cosine omega t, and we've come to the conclusion that if I can solve this related complex equation, if I can solve that, then I have a means for interpreting the solution that I'm actually looking for. So let's, first things first, let's actually solve now this differential equation. Okay, so here it is. Again, same equation. thinking about our undetermined coefficients method, looking at the right-hand side, I suppose we could worry about the possibility that maybe the a plus bi number on the right-hand side might be a root of the characteristic polynomial. However, notice that the number on the right-hand side is pure imaginary, whereas the roots of the characteristic polynomial here have a non-zero real component, because that's not 0. I'm going to leave the students to work out the details of that. Again, this is pure imaginary. This, because of that term, can't be pure imaginary. Therefore, there's no unfortunate coincidence of roots. So, looking at the right-hand side, we expect the particular solution just to be a multiple of that right-hand side. And here it is. I'm just going to take that right-hand side and multiply it by some unknown fudge factor yet to be determined. Now, students at this stage very often want to combine these two constants, t and little a, into a single constant. You could do that. It ends up being more convenient not to. So, very importantly, I want to leave this constant here visible as part of my guess. I want this t factor to be a separate thing, and we'll see the advantages of that in a few minutes. Okay, so we plug in and solve for t. This is a very direct process. You take this, you plug it in and go through, see what the differential equation becomes, solve for t. It's just like in section 4.3 of the book. And you're going to get some value. And you're kind of done at that point. Your solution is this. You solve for t, and there's your solution. That's your complex valued solution. And then, of course, the solution we're actually looking for is the real component of that. Now, we're not going to leave it in this form. It turns out that there's a neat algebraic sleight of hand that you can pull. It's very, very useful. This also is something students will find very handy. And it goes as follows. This number t that we just solved for, write it in polar form. Note that minus sign. We're going to have use for that minus sign, so put that minus sign in there. But other than that minus sign, this is just polar form. This is just saying that, look, if you have a complex number, that complex number can be thought of as real plus imaginary, but it can also be thought of as magnitude times e to the I theta. And that's all that we have here. Okay. So having done that, now let's write down what our actual solution is. So keep in mind this, that goes there, that becomes this. Of course, you can combine some terms here, and that combines with that to give you that. And so here's your complex valued solution. Now, so what? How does this help us? Well, don't forget what we're actually interested in is the real portion. Right, going back up to here. The real solution that we're interested in is the real portion of the complex z that we just found. Whoops. And the real portion of this is that. Right, the real portion of e to the power of I times some angle is just cosine of that angle. Okay. All right, so the reason that this is interesting is that, weirdly, the solution to the differential equation that we started with actually looks a lot like the right-hand side that we started with. Let's look back to it. Here, way back here, this was the differential equation we were initially interested in. Let's look at the right-hand side. It's a cosine omega t. A cosine omega t. Now, come back over here. Look at our solution. There's that a cosine omega t right there. So our solution looks just like the original right-hand side with two exceptions. One is that there's a phase shift. Let me do it like this. Phase shift. By the way, you can see now why we wanted this minus sign in here. We needed this minus sign in there so that that minus sign would be there so that we could then interpret this angle phi as a phase shift. Okay. And the other thing is that there is a change in the amplitude. Right? There's an extra factor of g in the amplitude. By the way, you can see now why we wanted to leave that a in there. We wanted to leave this a in there so that it would be there, so that the amplitude, the magnitude of that undetermined coefficient would be the factor change in the amplitude. And that's very convenient, so again, that's why we do that. Okay. All right. So it's interesting that the right-hand side of the original differential equation looks a lot like the solution. And that has an interpretation. We think of the right-hand side as being sort of an input to the system. Don't forget what the right-hand side was. The right-hand side was the external forces that are applied to the system. Don't forget our solutions. Our solutions describe the resulting motion, and you can think of these as sort of an input and an output. Given a mass on a spring, depending on what forces you apply to that mass on a spring, think of that as the input to the system. There is a resulting motion of the system resulting from the forces that you applied. So we think of that as the output from the system. So interestingly, in this case, what happens to that input to the system is just two things. There's a magnification of the amplitude, and there's a phase shift. So this magnification of the amplitude is called the gain in the system. This is a standard term, very common, gain. Again, conveniently, it happens to be this g, the magnitude of the complex undetermined coefficient, because of the way we set things up. And again, phase shift, standard term for describing that there. Okay. So by the way, don't forget that the differential equation that we're solving here, let's go back to it, way back here. Our original differential equation we were interested in, this is motivated, and we motivated this initially by thinking of a mass on a spring and how forces that we apply to this mass on the spring, namely determined by the right-hand side, would result in certain kinds of motions, which is the solution. Okay. But there are other physical systems that behave in mathematically similar ways, even if they're physically not very similar. So there are some similar equations that you can write down to understand, for example, audio amplifiers. And audio amplifiers take an input, which is a sine wave, and they produce an output, which is also a sine wave. And among other things, there's a change in the amplitude that is referred to as the gain for that amplifier. That's the result of solving a differential equation. And then there is a phase shift in the signal that comes out as well. So these terms, gain and phase shift, don't just apply to mass on springs. They apply to any sort of a system that's described by a similar differential equation. Okay, so very quickly, here's an example. Suppose you're looking at a differential equation that looks like this, and then there's the related complex equation there. Notice that the real portion of that is that. Right, so that makes this our related complex equation. And we're going to guess this as our particular solution. You plug that in, see what the differential equation turns into, and you can solve for t. And let's just suppose there's a bunch of arithmetic in there. Students should be prepared to plug in and see what kind of numbers you get out. Let's suppose that the number that comes out is this number here, 2 plus 5i. So what are the gain and the phase shift that result here in this original system? Well, following the pattern from the previous page, this number t, first thing we want to do is write that in polar form. Well, 2 plus 5i, right, gives us this number there. There's 2 plus 5i. And without too much trouble, you can determine the corresponding polar form. The magnitude there, g, is the square root of 29. And this angle, now keep in mind the angle is minus phi. Right, that's the angle for the complex number in question. That minus phi is that. Again, just a little bit of trig there. All right, well, now just like the algebra on the previous page, if you take this t and plug in to our, this is our solution, keep in mind, and a little bit of algebra and go through and see what you get, then this is your complex valued solution. Keep in mind the solution that we're interested in is the real portion of that, and you see that there's that square root of 29, that is the gain. Right? The magnitude of our t, undetermined coefficient, works out to be the gain. And the phase shift is, now you've got to be careful here, the phase shift is not arc cosine of 2 over square root of 29. The phase shift is the negative of that because of this minus sign. Okay.